Good morning, AP. Today I'm going to talk to you about a technique called mass spectroscopy. This is a new topic that was added to AP about 6 years ago. What mass spectroscopy is, it's an instrument called a mass spectrometer, that measures an atom's different ratios of isotopes. So we're talking about the same element, but looking at the element in different masses. And when you change the mass, that means the neutrons are changing, because you can't change the protons because the element is still the same. Because remember, protons identify who the element is. So this is the learning target, as you see right here, 1.2, and you have to be able to, by the time the AP test comes, you have to be able to distinguish between two things. So the mass spectrometer of a sample containing a single element can be used to determine the identity of the isotopes of that element and the relative abundance of each isotope in nature. And then the average atomic mass of the element can be estimated by the weighted average of the isotopes masses using the mass of each isotope and its relative abundance. So you need to remember about isotopes. So in an isotope, okay, what is the same? You have the same element, you have the same number of protons, and the same number of electrons. So what is different? It's the neutrons. And if the neutrons are different, that means the mass is different. Okay? So with isotopes, you have certain isotopes that are more abundant. So abundance. Okay? And you have isotopes that are less abundant. So if it is more abundant, what you would see is you would have like a higher percentage, okay? Or like less abundant would have a lower percentages. So think of it kind of like how you're graded in a class. What's your most percentage from your grade? Well, it's probably exams. So like usually 40–50% of your grade is exams. So that is more abundant towards your grade. So mass spectroscopy, what it is, as you can see the description of it, it's an instrument that uses masses to separate the samples of the same element. So they use high energy electrons, bombard a sample, which ionizes the atoms by ejecting electrons. And then it uses an electrical field to separate the ions based off their masses and charges. So it's what's called the mass to charge ratio. So a mass spec of some pure elements show the existence of elemental atoms with different masses, aka isotopes. So here's a sample graph of what a mass spec looks like. So let's say copper. Copper has two isotopes, copper 63 and 65. So remember with this number on top, that's the mass number. Okay? So if you have two isotopes of copper, are they in the same ratio? Well, we got to look at this graph called the mass spectrum. So if I have on the y-axis number of atoms, and on the y-axis number of atoms, and on the x-axis mass to charge ratio. So if you look at these two peaks, one peak at 63, so this is copper 63, and this peak right here is copper 65. Okay? Now, if they were in the same abundance, those peaks would be the same height, but they're not. So this tall peak right here, which means copper 63, must be more abundant because it has a higher peak. Versus this peak right here is a lower peak, so it would be less abundant. And come to find out, when you look at the y-axis, draw the line across, about 69–70% of copper 63, and on this one it's about 30–31, just draw the line across, okay? And then copper 65, 31% of it is from that isotope. So what happens is if you look at the periodic table for copper, the average atomic mass for copper, according to the periodic table, is around 63.5 AMU. And that should make sense for you. So if isotope only has two isotopes, but the average between them is 63, that 63 should be very close to the isotope that's most abundant. Okay, so that's how you read a mass spec graph. So we're going to do a lab with this week, and we're going to look at different samples, and we're going to draw mass specs, and we're also going to analyze using graphs. So let's look at a sample AP question. And if you want to watch this video, go on the team's website. At the very top, the tab that says CB videos, these are all of the College Board videos that they made in the spring. So look at the one that says 1.1 to 1.4, and starting about 31 minutes in that video, you should see the instructor talking about this sample. So this is boron, and boron has two isotopes, boron 10, boron 11. Okay, so notice the protons are the same because it's boron, but the neutrons are different, so that means it's an isotope. So if you notice the graph, boron 11 is more abundant, okay, completely more abundant. You come to find out with data, it's about 80%. So if you draw the line across, it's right there on the 80. 80% of boron, of its average, comes from boron 11. And this one right here is about 20%, as you see from the data right here. And this one, obviously, is less abundant. Okay? So if you were going to do the math for average atomic mass, okay? Now, I set this up in the typing it out, but when you actually write it out properly, because there's some units missing here. So you take each isotope. First thing is you have to take these percentages and get them out of percentage. And basically it's just moving the decimal 2 places. Okay, basically what it is. Or divide by 100. Okay, either one is fine. We just don't need to see you do that. Okay, so 20%. So we're going to go 20, and I know you only see one sig fig, but AP we don't do one sig fig. Okay, so we're going to pretend like there are decimals sitting right there. So 0.20 times the mass of that isotope. So right here you have 2 different isotopes. Isotope number 1, isotope number 2. And we're going to multiply it by the mass. Same thing, I'm just going to put a decimal there because there should be a decimal. So AMU. And you're going to multiply that out, and then you're going to get 0.80 times 11 AMU, okay, and you're going to multiply those out. Now, with these being 2 sig figs, AMU and AMU, okay, let me get my calculator. So that 0.10, or 0.2 times 10, so you're going to get 2.0 ATM, I'm sorry, AMU. Because we want to keep the sig figs going. And then if you have 0.80 times 11, then you're going to get 8.8. Okay? So if you add this up, you're going to get 10.8 AMU. Okay? So you always write the unit, the number, the unit, and the chemical at the end. Now if you look at Mr. Periodic Table, right there, that's the average atomic mass for boron. Okay? And it should make very close sense here, because if the average is 10.8, that means the isotope that's most abundant has an isotope mass of around 11. And it does. 80% of boron out there in the world is boron 11. So the key to this, the higher the percentage, the closer the average will be. So this 10.8 is being very dictated by this isotope 11. Okay? Here is another sample you can also do. So as you see right here, the College Board video, 1.1 to 1.4, and starting about 34 minutes, you can see this example. Okay, so if you have this one, the mass spectrum of element X. So basically, we're trying to figure out who element X is. Okay, and is presented in the diagram below. Based on the spectrum, what is the identity of element X? Well, element X has to have the same number of protons and electrons, but different masses. So as you see right here, 90, 91, 92, 94, 96. So this one looks like I have 5 different isotopes. Okay, but the key is who is the most abundant? Well, the most abundant is this peak. So that means my average on the periodic table should be very close to that mass of 90. So being this mass of 90 is the most abundant, and if you look at your periodic table, we try to find the element that has a mass that's very close to 90. But you also see that I have isotopes that are from 90, I have a range between 90 to 96. So if you look on here, yttrium looks pretty good. But if you look at one more element, zirconium has a mass of 91. So if I had to guess, using the periodic table, I'd say this element is probably zirconium. And according to the periodic table, 91.22 is the mass on the periodic table. So I know that I have an element that has an isotopes between 90 to 96. But these isotopes over here are less abundant. But the most abundant, 50% of this element is coming from mass of 90. So I know it's an element that's pretty close to 90, 91. And if you look on the periodic table, it's zirconium. One more example. Okay. So let's say you have this spectrum of Y, and we don't know who compound Y is. Okay. So the following 3 questions refer to the spectrum. So if I'm looking at this, I have masses between 92 to 100. Okay. So of this, let's see what I can distinguish. Well, it looks like 94 and 97 have the least abundance, but peak C, this one has the most abundance. Okay. So let's look at question number 1. So based on the spectrum of element Y, and this actually should say element, not compound. I think AP did a little boo-boo on this one. Based on the mass spectrum of Y, which of the following statements is false? So let's go through each one. Peak A and D come from atoms that have the same electrons. Well, this should make sense because if we're looking at isotopes, the same, what's the same? Protons are the same and the electrons. Every single one of these peaks, they all have the same electrons because they're all the same element. So definitely A is correct. So we're trying to find the one that's false. There are 7 isotopes of Y. Well, let's count. 1, 2, 3, 4, 5, 6, 7. So we got 7. That one's good. Peak C comes from the most abundant isotope. Well, we already said peak C, most abundant. So D's looking pretty good, but let's check out. So peak D comes from an atom with 4 more protons than B. So if you look at peak D over here comes from an atom with 4 more protons than peak B. So same thing as this goes right here. Peak D and peak B, they cannot be different protons because they have to be the same element. So this one definitely is false. Okay. Who is the identity of this compound? Same thing, it should say element. Okay, element Y. So we're looking at somebody that has the most abundance around a mass of 99. So if we look at that, let's see, 99 on our periodic table. Let's see, looks like, let's see, we got zirconium. Zirconium has a mass of around 91. We have molybdenum, has a mass of around, looks like around 95. And I'm just using the whole numbers. American down at the bottom has a mass of 243. So definitely not that one. And we have Einsteinium. Where's Einsteinium? Around 254. So definitely not even close to these two. Not even. So if you look right here, okay, zirconium cannot even be a consideration because you got zirconium somewhere over here. And we're looking at somebody with a mass between 92 to 100. So B, molybdenum, definitely a consideration. Okay, and we knew that our mass should be very close to 99. But because you have so many different isotopes here, it's not going to be exactly 99 compared to like boron, where you only had like 2 isotopes. So last question, which peak comes from an atom with the greatest number of neutrons? So the greatest number of neutrons has to be a peak that has the highest mass. So if you notice your peaks right up here, you have 92, because remember it's the same element. And if it has the same element, it has the same protons. So this one has the same protons, these all have the same protons, but why the difference is because the mass is different. And if the mass number is different, that means it's changing only the neutrons. So if they all have the same protons, then peak 100 would have the most, oops, not mass, I keep writing the word mass, the most neutrons. Okay, so peak D100, as you see right here, and just for clarification according to the video, same answers as we got. So hopefully, ladies and gentlemen, mass spec was understandable, and the point is, can you read a graph to figure out abundance? Can you read the graph to figure out or predict who would be the most abundance? And then answering some questions, doing some calculations. Okay, and we'll do some of these also in class. I'll see you on the next one.